Perfect. So we are a go. So thanks everybody for joining me for another one of our Siemens live webinar series. Today we're going to get an opportunity to explore the world of G-code programming specific to sub-spindle lathes. So we've done similar content in the past, but we've done it all around shop turn or conversational programming. So what I've been doing over the course of probably the past 6-8 months is I've been trying to then reintroduce the same content, but looking at it from a G-code side of the world. So that's what we're going to take a look at today. So we're dealing with sub-spindle lathes, so multi-spindle lathes, and how do I handle that sub-spindle, bring it over, all that good stuff. So I am your host for today, Chris Pollock. For those of you that don't know me, I am the Virtual Technical Application Center Manager. So what I do for Siemens is I develop a lot of our online content all around the topic of operation and programming, certainly some service stuff. So I am here as a resource for you guys. If you have any questions, concerns, issues, just need help navigating the world of Siemens, I am a resource for you. So you can always reach out to me, certainly by phone, but probably the best would be email. And like I said, I'm here to help. So with that being said, before we get into the main topic, there's a few things I want to kind of let you guys know of or keep you aware. I always like to promote the next up and coming events. We haven't done anything in the world of 808 in quite some time. So we are going to do a webinar on 808D milling and turning, and it's really specific to the built-in tutorial functionalities that a lot of guys don't realize is actually there inside of the control, inside of the 808 control. So we're going to take a look at the built-in tutorial as well as a lot of the integrated help functionality in the 808. Okay, so all of the webinars and a lot of the material you can find for us is located right on here, our main website, the CNC4U website. So for sure, you can always come to this website and check out what's coming up and get access to the older recordings. But one of the things that we've been finding is the more material we create, the harder it is to navigate this huge kind of library of content material. So what we did is we built what we're calling our content manager. So what I want you guys to do when you get a minute is navigate over to the CNC4U website. You're going to click the Education and Training and the Machine Tool Training link. And under there, just click on the Virtual Training, and it'll just give you a little pop-up. And there's a direct link for what we're calling the SINUMERIK CNC Content Manager. Now, this is certainly wide open to everybody, so you guys are more than welcome to share it with colleagues, friends, customers, whoever. But what you're going to get is you're going to get an Excel spreadsheet. And what it does is it has all of our content we've developed to date, as well as a mechanism to kind of guide you in what information you want to look at first. So you're going to fill out across the top here, you're just going to do a little pull down with this little drop down, and you're going to select the type of user you are, if you're new to SINUMERIK or if you're pretty experienced, the type of technology you're interested in, what's your programming method? Is it conversational? Is it CAD/CAM based? Is it strictly G-code? And then you're going to pick down the control type you're interested in. What will happen is this will automatically then highlight what we recommend the material you take a look at. And this is going to be not just webinars, but how-to videos, tutorials, all kinds of stuff in here. So I recommend downloading the Content Manager. Again, going back to it, you want to just go to Education and Training, Machine Tool Training, and then grab the SINUMERIK CNC Content Manager. Save it locally, and I suggest probably checking here maybe once a quarter or so. I try to update it on a quarterly basis just to make sure you have all the latest and greatest links. So that's something new that we haven't really had a chance to promote out to you guys. Now, we certainly still have our in-person training all hosted at our Elk Grove Village, Illinois facility. So if you're interested in it, go to the CNC training section, and that's your in-person training. And there you can not only see upcoming classes, you can register for the classes. We do have some new classes coming up. We hosted our first, which some of you may have seen if you're on our contact list, our first level 4 class or variable programming class. I hosted that. It's going to go between me and my colleague Randy Pearson. We'll kind of trade off who hosts that. But that's going to become one that's going to be a normal in our regular rotation probably next year. So right now we've been just kind of doing it as a as like a new class per se. But check it out there. But the other thing I want to show you guys is the Mr. CNC YouTube channel. So not a lot of you guys may realize this is out there. It's a great area to get a lot of material. You'll notice if you get that content manager I mentioned before, there are a bunch of YouTube links that'll drive you right to this site. But what we're doing is we're doing some additional type of video and online content beyond just the webinars like we're on right here, right now. So we're developing promotional videos. Those are usually 2 to 3 minute little promotional videos on key features and functions. We've got a whole series we're starting to do how-to videos. So they'll be a little more detailed. They'll be about 5 minutes long, but concentrating on a very specific feature or task. So the one you see here on the right is our tap recovery. So there I demonstrate you're in the middle of tapping a hole, you e-stop the machine or you reset. How do I recover or retract the tap out of the hole? And the other thing we're doing, which I'm pretty excited about, is we have a new YouTube live series. So so far I've hosted 3 events. So how that works is it's a little different than the webinar. First of all, I'm trying to keep them to around a half hour long, thereabouts. But what we have is we have multiple camera feeds. So we are actually streaming full camera footage live. So we're not limited to just the Sinutrain like you see here in these webinars. So we can really get in and work a machine, work a product. So I did a whole series on right angle heads. If you guys haven't seen it, by all means check it out. Then from there, and I'm just going to check my audio real quick. Does the audio sound quiet to you guys? Tell me if the audio's been going up and down, because my headset's been doing something funny. Nope, maybe it's just me. Nope, sounds fine. Okay, good. Thanks for that, Matt. Sometimes I'm flying blind here a little bit. Okay, so the YouTube live, it is a live event, but then similar to like the webinar we're on today, we capture the recording and it goes up on the Mr. CNC channel. So check it out and let me know what you guys think. And by all means, like them, share them, and follow the channel if you're interested in the material. But today we are going to, that's interesting, Mike said the audio's been going up and down a little bit. I might need to invest in a new microphone here. Well, we will work with it for now. Today we're going to be looking at features and functions that will support both the 828 and the 840 control platform. So really anything we talk about here would work on both controls. As we get to some more advanced features within these topics, then they will start to become specific to 840. But right now, sub spindle lathes can be supported in either control. So as I mentioned before, we're really concentrating on how do I handle a counter spindle or a sub spindle, and then how do we do kind of pick and place from it. So we're going to do the same part, and we're going to take a look at it in 4 different scenarios. First, a very simple, just grab it and transfer to the sub and do a back operation. Then we'll add a part-off cycle. We'll couple our spindles. We'll draw it. So we're going to go through the whole process here today. Now, it's always good to, I hear this audio going up and down. It's always good to kind of get your head around the kinematic setup of a machine, especially anytime you deal with machines that have a lot of spindles, because the commissioning from OEM to OEM is going to be different. This is an open architecture control, so our OEMs have a tendency to, kind of change around the machines quite a bit. Sorry, guys. That isn't super embarrassing. I had it muted. So step 1, whenever you're working on a multi-spindle lathe, take a look and see what the axis designations are, specifically for the spindles, because that's very important. You're going to need to know, what is the main spindle? What is that OEM calling it? In this example we're working on today, it's SP1, but it could be referred to as a C-axis. It could be called anything that really the OEM wants it to be. So we got 3 spindles on this machine, SP1 being our main spindle, and SP2 being our counter spindle, or in this country, a lot of times we refer to that as our sub spindle. And then SP3 is going to be the live tool. So we're not going to really deal with SP3 today. We're concentrating on the main and the sub, so we're looking at SP1 and SP2. Now, the other axis we're introducing here is our sub-spindle, the linear axis of it. So it's pretty common to see that denoted as a secondary z-axis, because if we think of the nature of z, they kind of both go parallel in relation to the spindles. So here, this one was called Z2. It's pretty common that it's going to be called something like that. Now, the first Z may be just called Z like it is on this machine. It could be Z1. It could be some other slight variant thereof. But those would be the three primary axes we're going to take a look at today: the main spindle, the counter spindle, and that Z2. Now, when somebody, an OEM, commissions a machine, it's really important that they kind of follow this logic. They don't have to. The control allows you to set them up, of course, for all sorts of different ways, but this is the best way to start to set up a machine. And what it is we want to have a fixed datum for our machine 0. And generally speaking, you want to have that based off of the main spindle. So what that means is if I was to drive my turret to position where all the axes read 0, my turret would basically be touching the face of the spindle. Now, and a lot of times you may not be able to physically get there, and that's okay, but all the offsets should take precedence from that point. So this way, it makes it really easy for kind of handshaking between all these other linear axes that are moving around for us. So machine datum is going to be the front center of your spindle. Then from there, we're going to just really kind of take a look to see what's driving from there. So my Z2 is going to drive that sub-spindle, as I see here to the right. X and Z, they're going to handle moving my turret out of the way. And then my spindle 1, spindle 2, that's just going to handle my main spindle, sub-spindle, physical chucks when I start inducing a rotation there. So to our right, this gives us, again, the axis designation. Now, when you use the machine from a jog perspective, you are going to get a few extra axis designations once you're on these multi-spindle lathes. So what you'll have in the TSM screen or in our TFS field, which shows us our feedback of our display, you're just going to get a simple pull down. If your machine happens to have a touchscreen or a mouse, you can click on it, or you can tab over to that location and use the next window button to kind of move around between the different panes if you don't happen to have a mouse or touchscreen on the control. But you'll do a pull down, and then you can really derive with the select key which of the spindles I want to either command, that would be through the TSM screen that I see here on the left, and then which of the spindles I'm going to be viewing. So just because you started spindle 2, right, and I said, turn it on at 500 RPM at a specific M code, you may not see it in the TFS display until you toggle that or pull that down. So if you take a look here, and I'm just going to jump to Sinew Train real quick. This would be a standard machine the way I would see it inside of the jog area, right? So we have our X, Y, Z axes and our spindle locations. Sometimes you don't have enough, view or room in this window, so then you get a little pull bar. Now I'm using a mouse, but if you use the next window button, if you're on a machine that doesn't happen to have a mouse, you can see as I click the next window, and then I can bring my arrows up or down, you can still fully navigate this control without a mouse or touchscreen for sure. I'm going to certainly take advantage of it and be lazy. But here we see all our axis designations. And what I was talking about with, if I want to drive spindle 2, let's say, and I want to turn it on, I need to go to TSM, and under TSM, I'm going to get this pull down. And I can, if I just, move my cursor down here with my arrows just to show you the keyboard equivalent, I highlight it, hit select, and then I can come down and choose a specific spindle that I'm going to run, drive an RPM, maybe give it a direction would help, cycle start. Now, is the spindle running? Is it not? So just for real estate purposes, we're not going to show you all the spindles, but if you come up and view the spindle, then I'm going to see the state that that spindle's running in. So here I'm running 500 RPM in a counterclockwise rotation based on my selection. Certainly I could have driven that through G code as well, and we will be here shortly. I just wanted to give you guys kind of a feel of what the multi-spindle environment is going to look like if you haven't had a chance to really get on one and run one yet. Okay, so now that we've kind of navigated a little bit from the jog perspective, Let's kind of take a look at our use case and how it would be set up on the physical machine. So in our case, when we're all said and done, we'll have machined a blank and made it 100 millimeters long. We're just going to machine 2 basic bosses on it. So when I first lay it out, I really want to think about my nesting, because it's real important once I introduce the counter spindle and I go to grab it and I want to kind of pick and place things, knowing where the part is in space. So remember, my datum is the back spindle face. So I have a couple constants I have to deal with. I have a chuck body thickness, I have a jaw projection, and then I'm going to have some kind of desired projection of my part to accommodate certainly enough room to machine it without driving my tool into my chuck. Then I'm going to think about how I want that part to sit in the second spindle once I've done the transfer. Once I come over, because I got to make sure that I pull it back in a known location, or my zero may be in a completely different spot. So there's a couple things that I really need to kind of pay attention to. Where am I sending the Z2 when it's done? But additionally to there, how much did I throat the part by? All of this can affect where the second work offset is, because I'm going to have 2 work offsets when I'm all said and done. I'm going to have a G54 most likely, and then in this case I'm going to use G55 as my secondary work offset. And I need to know where that's going to fall in space. I do want to also anticipate a safe location to send the turret, because if you think about it now, I got this sub spindle moving around, so I have a lot more crash potential or collision potential when I get to that. Oops, I clicked the page. So you're going to want to have a known safe location. That's something that you really kind of have to be on the machine and see how all of your tooling is kind of laid out and see where you can send that turret to be in a safe position. Now, when we start setting up the work coordinates, generally speaking, we're going to really just have a Z offset in our first and then eventually in our second work offset. I myself don't assign a secondary work offset for G54 and Z2. I let my Z2 kind of drive in relation to my Z work offset. So you're gonna get a chance to see that when we try to move it around. So it's actually moving relative to machine 0 when we move the Z2. Now when we get to G55, it's important to pay attention or make note that not only do we have a work coordinate shift, but we also have a mirror that's being set up at the work coordinate level. So you see in G55, we have a checkbox here under mirroring of Z, and what that's going to do is that's going to take all of my geometric data that's moving in a Z direction and flip it 180 degrees. So the beauty of this is whenever I'm programming the machine in a Z negative direction, I'm always going into cut, or I'm always moving towards my work holding. And the actual physical motion of the machine is going to invert itself as I bounce between the main spindle and the counter spindle. So if you have common tool paths, like for us, we have a very simple tool path that machines our boss, I don't have to reprogram the tool path. I think more importantly from my own mind, it's easier to always think negative towards work holding, positive away from work holding, and I don't have to change that as I move between 2 different spindles, right? My main spindle or my counter spindle. So that's what this mirroring is going to handle here for us. That's going to handle inverting the Z-axis. So from a programming perspective, I always think Z towards work holding plus negative Z towards work holding, positive Z away from work holding. Now, when we use it, and you guys, if you had the opportunity to see this session in ShopTurn, there's a spindle chuck data area under the offset of the parameter page. And that becomes extremely important because the system in ShopTurn will calculate automatically where it's going to pick and place. When we get to G-code, this is all manual. So although you can fill out this data in this page, and I suggest you do, just kind of keeping your head in the same process, G-code doesn't use any of these values. Now, these are all writing to system variables. So at some point, if I wanted to pull these numbers, you certainly could. A little later in this session, I am going to show you how you can start to use some basic variables to simplify this type of programming. But at the end of the day, this is really just derived for ShopTurn. So any data I put into this little subscreen, it's really not going to be used unless I go the next step, find the system variable, and start pulling from it. But where that is, just so you guys see it. It's under the offset table, under setting data. There's a button called spindle chuck data. And this would be where I can type in my jaw types and basically my projection of chuck body and chuck jaw. So I get into the habit of always setting this up, whether I'm doing straight G code or conversational, but really it's not being used from the G code side of the scenario. So we're starting to move forward a little bit. We start to think about what we want our part to kind of look like, where we want it to nest. It's important to think about not only the finished overall dimension of the part, but what the rough stock of the part length is as well. Because you're going to be taking off that dimensional data, you'll be clearing off some kind of facing material probably from both the first operation on the main spindle and the second op on the counter spindle. So we want to anticipate and think about that when we're going and grabbing. Generally speaking, when I start to work on a job like this and I find myself kind of chasing myself as far as, gee, why is my zero not where I expect it to be? Why is my tool not touching my part, or it's taking too heavy a cut? It's because I didn't anticipate the amount of material I'm leaving for my roughing, what my finished dimension is, but also what my rough dimension is in Z. The projection is very important in both work holdings, especially because I want to keep from colliding. But more importantly, when I pick and place, I need to have a known location to drive the machine to. Now, as far as from a tooling perspective, generally most of these turrets, they were established on a known datum to that spindle face. So it's not uncommon at all for the center line of the live tools, especially any of the live tools pointing down towards the, in the x-axis direction. That center line would be Z0. So if I sent the turret all the way to machine 0, it would be dead center of that turret face. And then from there, if I'm just working off that tool, I don't need to necessarily put a Z offset as long as the center line of that spindle is on the center line of the turret. So then I just give it an A offset projection in my X to compensate. So that would be very similar to this tool in tool number 1, which kind of looks like a facing tool, or my drill in tool pocket 15. I'm just going to give it that X or that X distance offset to then compensate for the projection length. If you're dealing with tools that are oriented in an axial orientation, not in a radial orientation, then you're going to have to deal with an offset in A and B. But again, all these offsets, it's really similar to setting up a mill with positive tool length offsets, right? They're distance from a known datum to the center line of the spindle or out to the tool tip would be the value I would expect to see in the tool offset table. Okay, now what do I have to know about this machine specifically when I get to programming this in G code? Well, really the big unknown, generally speaking, is what M codes did the OEM assign to be able to allow me to drive the chuck open and close? And I have a couple different conditions, right? Can I open the chuck when the chuck is not spinning, but also can I open the chuck while the chuck is rotating? Generally speaking, you don't usually want to open a chuck while it's rotating, but if you're going to do some kind of live transfer, or when we get into doing a part-off operation, chucks have to be spinning. So here, I'm going to use, there's a combination of 4 M codes. 131 would allow me to open the chuck in a non-spinning state, and that would be the main spindle. So usually what you'll see is index 0 is going to be the main spindle. Index 1, so that 22,550. When we refer to index, that's just that number in the brackets. This one would be opening the chuck, the main chuck, so 131. 52,250, index 1 would be opening the chuck, and my sub spindle or counter spindle. And then 132,232 allows me to open while rotating. And then 130 and 230, it's the same M code to close the chuck, whether it's spinning or not. So how I got to these M codes on the control is I'm going to go to the actual setup parameters area. So we're looking for 52,250, right? So if you go to menu selected, the control, go to setup, you want to enter the machine data area and go to channel MD. And under channel MD, if I search for 52,250, this is where we list all of the M codes associated to a chuck. So it's just a nice central location for you guys to look, because a lot of times you might not realize what the M codes assigned by the OEM are, and here they are, straightforward list. So this is fully customizable. This doesn't mean this is going to be the same M code numbers that you see from machine to machine, but generally speaking, most OEMs set them up right here in this location. We're pulling for this area, especially if you're going to set up the machine to comply with shop turn. So that's generally why you would see all of these in there. So when you're starting these, go into the, make yourself a little cheat sheet, write down your axis designations. What's the main spindle axis name? Is it S1? Is it C1? Whatever. And then also go in and make yourself a little quick list of the M codes associated to which chuck and what state they would be open, because you're going to have to pull from all this once we start writing some programs. Now, creating a program is going to be straightforward. It's going to be similar to the way we've created programs, in any other environment. We're going to navigate to our program manager. This would be the basic part. Again, I said intentionally the part's simple. Toolpath. This webinar has nothing to do with toolpath, right? This is all about the process. So in this case, we're going to machine a simple widget, simple boss, so to speak, where we have two hubs. Each hub are going to be machined from 100 millimeter down to 50 millimeter diameter, and they're going to be 40 millimeter in, and the overall part length is going to be 100 millimeter when we're said and done. So go over, get the program manager. We're going to launch a program. We're going to certainly select new, kind of drive it normally. But before we get too far into it, let's take a look and see what the desired operation is going to be. So here we're going to machine a basic boss. We're going to go grab it. Actually, I think I did it out of a smaller diameter than that print. Yeah, I did. So it was a 50 mil diameter OD, machining it down to 25. Again, the shape is just a shape. It's really the process. So we're going to machine, run over, grab it, and retract back to a safe position. So when it comes time for me to kind of calculate where everything is based on my work holding, based on my projection distance, we created, here we're going to go in, create a new program. I guess my slides sequence could be a little better. So we've created a little Excel spreadsheet that's available for you guys. So if you guys are interested in this, if you get into this type of programming, reach out to me, send me an email. I'll bring my email again at the end if you didn't catch it earlier. But this is a sheet we'd be happy to share with you that allows you to calculate, and it'll actually calculate for you what your work coordinate values are going to be and where these parts are going to end up in space as we kind of set up all our nesting. And this is key. You're either doing this by hand and you're drawing yourself a little scratch sheet, or you can use this Excel spreadsheet that actually a colleague of mine created in Germany, did a really great job on it. So for us, if I'm going to go set up a job, again, I got to think of all these numbers, right? So if the machine 0 is the back of my chuck on the far left, well, then I have to accommodate a projection. So we had said earlier we had 89 millimeters for the chuck body, so I can plug that here. And what you're going to do is anywhere you see green, that's where you're going to fill out. Anything that's red is calculated for you by the spreadsheet. You can fill out the greens on the side, or you can fill them out in these fields. So what you're going to do is fill out your chuck dimensions, draw dimensions, and how much you want the part to stick out, accommodating for the material you want to take as a facing cut. So in this case, I said I want to face off 1 mil. Maybe it's saw cut, it's rough, whatever. So I'm giving myself 1 mil. So initially, it's sticking out 60 mil, but once it's cleared off, the actual datum, or 0, is only 59 millimeters out. So, just think about that when you come to your nesting. I'm going to tell it how much material I want to leave on the opposing side. So I'm just going to do 1 mil to keep things consistent, but it doesn't have to be. I am not going to fill out the projection distance. I'm going to let that drive from a value down here. So we'll get to that in a sec. I certainly want to tell it my counter spindle jaw projection and body width. I just use the same chuck bodies for both. We're saying maybe we have 2 10-inch chucks, 1 on each spindle. But I do need to give it my rest or park location. A lot of times we refer to this as the park location. This is where I'm going to send my sub spindle to basically stop and hold while I machine any of the operations in that secondary clamping, right? So when I jump around, come back to it, start machining the back op, I'm going to want to send the spindle to a known position. Now, additionally to this basic information, I want to tell it two extra pieces of information. I want to tell it my initial stock length. So again, remember I said we want to end up with a 100 millimeter long part. Well, if I'm leaving 1 millimeter on the front and the back to face off, then that's why I would put an initial stock length of 102 mil. And then I want to tell it how much I want to throat or come over and grab by my jaws. So really what this dimension would be from the jaw face into the end of the part. Remember, I'm at a finish point. So here I'm just going to tell it how much I want to grab. I was grabbing 21 mil. From there, the system's then going to calculate a couple things for me. It's going to calculate, or system, I mean the worksheet, it's going to tell me what my work coordinate would be in G54 based on all of these stacked offsets. It's going to tell me what my work coordinate is going to be for G55 once the subspindle's back at its parked location. So what all it's really doing is it's taking into account when I'm back at 1,000 millimeters away from zero, it's subtracting the chuck body, it's subtracting the jaw projection, it's subtracting the overall part length, and then adding the stock that I'm going to take, and it's calculating this number. So again, you can do all this longhand. The sheet's just going to work it out for you. And this is going to tell me what value needs to be put into my work coordinate system. And then the other thing that's real important is this transfer position that we calculate right down here in the bottom. This is the location based on machine 0 that we're going to drive the counter spindle to when I grab the part and move it back. So generally speaking, when I go to pull back, if my tool's not touching or overcutting, I messed up this number. And I either messed it up because I didn't accommodate for stock properly, or one of these values didn't work out. But this is that magic number. This is where I'm driving the counter spindle to during the part transfer. Hence why we call it transfer position. So again, if you guys are interested in getting your hands on this worksheet, send it over to me. Send me a quick email. I'd be happy to attach it. So from there, it's time to start writing a part program. So in the program, I have a couple new variables that you guys might not have seen before. So we just calculated the G54 and the G55, right? That was done by the worksheet. So I could leave it up to the operator to type those numbers in. What I don't want to do is I don't want to let him just come up with any arbitrary numbers. Because if you can think of all of this nesting, right, all this stuff we have going on here, if they change any of my work coordinates, it's going to render this part program non-usable. You would have to adjust the part program to compensate for where all these offsets are in space. So what I like to do, since I have known values, and I'm working this from a real machine, we'll say, I'm going to write them right from the part program. So this is a quick, simple way for me to write to the coordinate system and write directly to the first work coordinate. That's why there's a number 1 here. That would be G54. Which component I'm writing to. So remember, we're writing to the z-axis. And where within the z-axis. So the TR designation means I'm writing to the coarse offset. So this line right here, that will then take 199.625 and automatically drop it in to the G54 field of Z, which is really where I need it to be. So you can do this, or certainly you can have the operator type it in, but it does have to get put in there at some point. The next is then dropping in my G55. So that's why you see I have a number 2 here. So that is my work offset number 2, which happens to be G55. And then the Z and then the TR again means coarse, because I can direct these values into the coarse field, into the fine field, into the rotation, the scale, all by using a slightly different designator. So I'm using TR. And then what I wanted to do is I wanted to also make sure that the operator didn't forget to mirror the z-axis. Now this method will not delete any other components, so we do have to make sure that all other offsets would have been zeroed out in that work frame, but it is turning on the components I need during this job. Okay, so once we've set up the work coordinate, now I can go in, do a standard safety line like we normally would. Diameter mode on just tells it that all x-axis values are diametric values. I use the workpiece blank here just to set up my graphics for simulation purposes. And really the new thing I'm doing now is I'm driving the counter spindle to a safe location. Now, if I'm not going to be machining at this point, I don't need to send the sub spindle or the counter spindle right to the 1000, but I'm going to need to get it there when I go to machine. So generally speaking, that park position is where you just consistently send the sub spindle to anyway. And since these numbers are based on machine 0, I can just call them right out in my super line. And there's no offset, right? I haven't written anything to the Z2 field in G54. So that's where she's going to drive. She's driving 1,000 millimeters from the machine 0, which is the face of my spindle. Load by tool, we're going to set our main spindle. That's just assigning the M codes, or what's the primary spindle doing the spinning of the work holding. And when you get to multi-spindle machines, you do want to then assign the S and M codes to that spindle. So if you just do the set main spindle index 1, you could get away with just typing S1200 and M3 and it would work. But generally speaking, I like to keep the format consistent because we're also going to start to drive our other spindles. So you can additionally just say my S code for spindle number, and that's where this number 1 comes in, equals 1200. And my M code for spindle number 1 equals 3. So this is the same thing as saying S1200 M3. And now once I get to this format, then I can drive that to any spindle. So if I wanted to fire up my live spindle, I could say S3 equals 1200, M3 equals 3. And that would be M code for spindle 3 equals an M3. Okay, so that's the start of our program. Pretty standard of what we've done up till now. Position in the tool, take a little face cut. I used cycle 951 to handle our turning. But when we get to it, this is where we're going to start to deal with the actual transfer side. So I want to make sure I send my turret to a safe location. That was that position that we were kind of looking at. This is a value that you're really going to have to take a peek at once you start to move the turret around and are on the machine. I am reactivating my tool offset because I killed it during my suppression. I'm using the M commands like we just talked about to make sure both spindles are stopped. And in this case, I want to just throw up a simple message so the operator knows to remove the part from the counter spindle. So I'm assuming on this machine I don't have any kind of shuttle robot that's going to pull the finished part out of my sub spindle. If you do, you don't need to do this process. And then I'm just putting the machine into a program stop. This ensures that I don't try to take a spindle with a part in it and come over and shove it on top of another part. Now, since both spindles are stopped, I can open up the counter spindle with my M231. So that's using that 231 we found from the original M code. And now I'm going to drive this counter spindle, my Z2, to a position just off of the clamping location. So if we can remember earlier, when I looked at the little spreadsheet, let me get back to it real quick. The machine, or this spreadsheet, calculated a transfer position of 319.25 millimeters. So what that is we know where this part exists, but I remember I have to compensate for the chuck and the jaw, right? So I have to move out. Because if I was to send this chuck right to 199, that would be the back of the chuck. So I'd have two chucks buried into each other. That's how it calculates the 319. It's really just taking the jaw and the chuck projection as well as my throat distance into account to make sure that my jaws are sitting in here by 21 millimeters, hence my grab location. So initially when I'm moving that counter spindle up, I don't want to go obviously right to that position. I'm probably going to want to feed to that location. So I'm going to rapid just off of that. So I gave myself a little bit of room. And then I'm going to drive the machine to a feed location. And what I am doing is I'm changing my time base. So a lot of times, and in this case I have to, remember my spindles aren't spinning, so I can't be in a G95. So we select G94, feed per minute, and then I'm running it in at 500 millimeters per minute or whatever feed you're comfortable with for sure. She gets into position now, and at this point, we then want to fire with our 230 our jaws to close, right? So we've come in, we've grabbed the chuck. I like to add a dwell here. The OEM may have accommodated for this, but just in case, those jaws take a little bit to move, right? They got to come down and grab the part. So what you want to do is want to give yourself a slight delay while the jaws are closing. So I'm giving myself 1 or 2 seconds. A lot of that will depend on how fast the chuck moves and the throat or the travel of the jaws. Once I've grabbed the part, now I got to think about, well, what's my next step? All right, so the next step is probably open up the main spindle, hence why I'm giving it an M131. Give it a slight delay to make sure I don't start pulling on the part before the jaws have released. And then I'm going to wrap it back to my Z2 of 1000, and that is my park position. So this way, all the other offsets are going to take into account. So, if you get an operator who says, oh, I don't want to send the subspindle back quite that far, I want it closer, I'm just going to edit this number. Well, that's going to mess everything up, because next you have to also combine that in the work coordinate for that position. Once we're there, load up G55. And this is kind of a neat command, and this is just for graphic purposes. But if you guys are maybe methodizing a post processor, and when you're simulating, you want the view window to change from the main spindle to the sub spindle automatically for you, you can use this workpiece command and then this set focus number 2. And the number 2 is directing the focus to the secondary spindle. So if you just mimic this exact string length, so you want to add these 3 commas, quotes, set underscore focus, end quote, comma 2. You'll see in a second when we simulate, it'll automatically change my view window. But just simulation has no bearing on toolpath. Now, this is going to be my process step, right? So we're going to machine the part, come over into a pre-position. That was my 430. Feed to that transfer location value. From there, open up the next chuck jaws, pull back, get to my park location, and continue on. Now, when I get to that back location, once I've retracted the counter spindle all the way back, now the system's going to use the work coordinate that has the mirror in it. Right? So that's my G55 I've loaded. I let the system variables program all this for me, but I do want to make sure I am using a tool that is a right-handed tool as opposed to a left-handed tool, or whatever the appropriate tool for that counter spindle would be, but I can use the same tool path. Because remember, negative is always towards my work holding. So I could literally copy and paste or call up the same subroutine for argument's sake, and then drive the exact same tool path on that sub spindle because of that nice little checkbox right there. So we want to switch back to G95, obviously do our tool change. Here I'm going to use a set MS open close parenthesis number 2 because I'm saying now my primary cutting spindle is going to be my sub spindle or my counter spindle. Fire up my counter spindle with the M2 equals 3. So that's M code for spindle number 2 equals 3 for clockwise. S2 equals 1000. We fire up our G95 and then I come down, and really this is going to just duplicate the toolpath I did on the other side. Machine up my part. So if everything's happy, we should have a finalized part. So let's take a look at this program and we can kind of dissect it a little bit more. So initially, let us get rid of some of our work offsets, and you can see where this all comes in. The mirroring, you do have to hit your details field to get to it. And now I'm unchecking the mirroring and my little symbol goes away, right? And if I look at the program, here is the program we set up. So first things first, we want to use our system variables, PUIFR, to write to the frame variable for work coordinate 1, the Z field in course. Then we'll do the same thing doing G54 or G55. This handles our mirroring, and then we come down through. So if I was to just start the part program, and maybe we'll do a single block, we just get past this section, we're down on our workpiece blank, then you'll see immediately we wrote to the coordinates I just deleted. So this is really just taking some of the some of the necessity of your operator to have to worry about typing this in, and God forbid he had a typo when he did it. From there, we're going to drive the sub spindle, so wherever she was sitting. So let's say for argument's sake, we'll go out to jog for a second, that my sub spindle, and see, I can't see it until I scroll down. My sub spindle, some of the location, right? I'm at 747. So when we are in auto and we start to move it around, once I get to my Z2 equals, I'm going to see this Z2 axis go to that known position, value off the machine coordinate system, and then we're going to continue down through the part program. So let's take a look at in the simulation mode. So if I simulate our operation, this is going to be kind of what the operator sees. So tool comes down, starts machining our part. So at this point, my sub spindle should be sitting all the way back. Here's my little message command prompting the operator to make sure that that is clear. And I am going to just zoom back so you can see where this sub spindle is. So let's pull it all the way back. And, so there she is, sitting all the way back at 1,000 millimeters. Now this scale is going to be relative to G54. That's why I don't see the 1,000 here. But if you kind of look at the hash marks, you can see it equals basically 1,000, because right now we're sitting at approximately 200 millimeters out, right? It was 199 and change was our work coordinate. So the next step, once I hit cycle start, system's now going to come over and grab the part. So there's your transfer, and then see it happened kind of quickly, but see how our focus now jumped right to the sub spindle for me? So that was that workpiece focus. Had I not had that function, so down here, if I left this alone, right, or we just comment it out, from a simulation perspective, it's going to sit at the main spindle. So nothing's kind of directing it to change. So in this case, if this was my view, it's going to actually hold this view the whole time. So let's cycle start. She comes over, pulls back. Now we're working on the sub spindle. But if I want to get it to bounce back and forth, so this is kind of a nice thing from a post-processor standpoint. You can add that little refocus in. But there, we've done the full transfer. So if I had any problems throughout the process, I'm going to see it right here in simulation. So let's say for argument's sake, I decided, my operator comes down and says, hey, after I do my retract to my park location, 1,000's too far away, I change that to 800. This is where we're going to see everything goes haywire, because all our numbers are based on a known location of that sub spindle returning to. Also us knowing everything about the geometry, the work holding. You know, the guy goes and changes his chuck jaws and doesn't tell you, and the part's sitting in a new location. Now I got a problem. So here she's still going to try to machine as if the part was there at 1,000. So how would I fix that? Well, now I'd have to change that value right in the work coordinate system, right? That's a direct result of this work coordinate. So this is a relatively easy fix, but you know, it gets a lot more complex quickly depending on, you know, if I'm shifting the part around in the main spindle, or if I wanted a different throw to mount in the sub spindle. So working from either, you know, that spreadsheet I talked to you guys about, or just kind of mapping it out and drawing it for you is hugely beneficial when you start dealing with this type of technology. Okay, so hopefully this starts to give you a feel. We're going to now introduce a few new commands, because this was a very simple pick and place scenario. So the next step would be to maybe integrate a part-off cycle, because we're working from bar stock, right? Very, very typical that I would do in this scenario. So this would be what the toolpath's going to look like. So in this case now, we're sticking the part out significantly longer to accommodate for that part-off operation. Now I'm going to bring over the sub spindle to support the part during part off. So we're now going to move things around and couple the spindles, and we're going to be able to open and close the jaws while everything's in a running state. This probably is not an ideal scenario to machine the part, because everything's sticking way out, but you could do it. So this would be a process step. But watch what happens with the part off. You see how little is left out of my chuck jaws? So in this case, I would at the end need to have some kind of part advance before I can machine the next part. whether it be a bar feeder or some kind of a bar puller. I didn't add it to this part program, but just be aware of that. If I wanted to fully come over and start cutting the next part, well, she has to be sticking out the 60 mil or 50 mil, whatever it was that we had it sticking out from. So instead of sticking out, in this case, 120, it's really going to have to be 100 plus another 50, so I'm going to stick way out in this strategy. So how do we handle this? Well, first things first, I need to change my nesting strategy a little bit. So here you see, I'm now going to push out my projection. In this case, I was saying just 120 mil, and that's going to directly calculate a new G54 for me. Now, just by pushing this out, it's not going to change where the sub spindle is and where everything else is going, as long as my nesting is the same, but it is going to change my transfer position. So now I'm at 379 as opposed to as a 330 or something before. So that's where you can start to see how there's so much dependency on these numbers as I start to plug them in. So what are we adding here? So the header of the program is the same. There's no point in going through the entire program. It's all the same stuff. What I've done now is after my safe retract before my transfer, I've now added in a tool change to go grab a part off tool. I'm still going to do the same safety to make sure that the part in the sub spindle's out of the way. I can turn on both spindles with an S1 and an S2. And it's okay if, it's previously it was set to, set main spindle to number 1. That's all right. That's why you're using the numerical designation to direct the S codes. And then from there, I start to use this couple command. And what that does is that synchronizes the two spindles. Because the last thing I would want to do is bring over the counter spindle, grab onto the part while the main spindle's spinning it. If they're not perfectly synchronized, they're fighting each other now, right? If one was going 1,000 RPM and the other one was going 999, that's a problem, right? So that's what this coupling command does. It does two things for us. It allows me to make sure they're both going the same RPM, and one is slaved to another, but it also would allow me to apply an offset in case I had to anticipate for nesting of the jaws, right? We're way away. It's not an issue. But if I'm doing a grab where my jaws could collide, then I could clock the jaws and let them kind of nest in between. So to use the coupling command, you're going to do a couple things. First, you're going to define the coupling strategy. That's with this COUPDEF command. That's always first. And under COUPDEF, we're going to stipulate our slave spindle first, and then our primary spindle. So that's the FS designation. It's what we refer to as the following spindle, right? So it's a slave to the main. The second one is going to designate my main spindle. Then from there, I do tell it if there's a ratio between the spindles, and typically there's not. So this is usually a 1-to-1 scenario. So you would make these next two values 1-to-1. But if there was some kind of ratio difference for them to couple, that when spindle 1 goes 1,000, spindle 2 is only going 500, then I would have to add what we refer to as the numerator and the denominator here. The knock command, honestly, I've never really used any of the other equivalents to it. It just says that I can execute this immediately instead of delaying. And then same thing for this set point linkage. The default is DV. It's a coupling type strategy. Again, I've never seen an application to use one or the other. So I always use knock and DV in the definition command. Now, the next thing is then actually activating the definition of the coupling function. So it's coupling on, so COUP on, and then it's my following spindle, my lead spindle, and then this 90 degrees, this would be my offset value. So you do need to know where 0 would be on both spindles. You could just, command both spindles simply with an SPOS command or tell it that axis to position to 0. Manually jog it up, see how they look, and then start applying some offset to it. So there's a 90-degree offset I gave it. Again, our jaws are nowhere near each other, so it's really not that big a deal. Then we can fire up or open our counter spindle. That's our M232. That's going to open it up while in an on state. We drive it over, we do what we're going to do. So that's going to be all the same, really. Now the difference here is when I'm done, I want to turn my coupling off. Because I'm turning my coupling off, my part's already retracted. I've already parted it off at this point. That was all through this middle section. And then I want to shut that off so this way I can shut off my main spindle and I can just keep on working on my sub spindle. If for argument's sake I was going to immediately come back and start cutting on the main, then I might not want to shut it off per se. So let's go look at it. This is going to be, this is a part transfer with cutoff cycle. Yep, so here you can start to see this will be what the structure of the code would look like a little bit more. So our couple command, open up our counter spindle position. Here I'm accommodating the new location because we're sticking at 120. We're going to close our counter spindle while the main's still running. So now they're synchronized and I'm supporting the part. I'm going to use a basic CAN cycle for our cutoff cycle. So that's our cycle 92. This should certainly just be G code driven from your CAM system. Then we're going to, once parted, retract to our safe location, disable our coupling. So I certainly want to make sure that I'm parted and retracted. And once I stop the coupling, now the two aren't synchronized anymore. I can keep them both running. In my case, I'm just going to shut off the main and we're going to duplicate the process that we did before. So here would be the operations. You know, I'm sticking way out. I come on over, I grab it. The spindles are both spinning. Tool comes on down, parts off. Then I retract, and then it really machines the exact same tool path as we had before. So let's jump to it and take a quick peek at this program. And if you guys ever want these examples, these are great, real basic programs to start all this. Just email me. I'd be happy to give you the actual programs. So here we're now in that new location. We have that compensated Z780. If you look, this exact same programs we had before, only difference is now we have tool change, fire up both of our spindles, make sure they're both running, jump right into our coupling command. Then I can start driving my spindle state. So I want to make sure that this chuck is open. Come on over to now in this case, I used a little bit of, I did a little formula here as opposed to, this would be my rapid slowdown. I'm just saying, hey, whatever my transfer position is, add another 60 mil to it. So it's just a little cleaner way. I can use the same number in both positions. Really, the key is this number right here, right? That's where the jaws are going to go grab the part, close it on up because now both spindles are spinning, so I can handle my cutoff operation, retract, disable my coupling, and we can continue on. So really the downfall again with this method is the fact that, and if you watch it, and I'm going to slow down the override a little bit. So here we're cutting our part, and then we're going to come off and part it. So if you look at how much, we grabbed it, we're spinning. So I don't have enough material there to cut the next part. So I would have to add some kind of a bar feed scenario to get it out, or maybe a bar puller or whatever. But there would be another operation required if I wanted to come down and then machine the next part or the next piece in my production run. So what if I want to do the same job, but I want to be able to then draw out. So instead of sticking the part way out in space, I could still stick it out a nice short amount, have it stable, machine it. So then we add in just a couple extra commands, and now I can go in, grab it, and draw the part out. So that, again, working out the same tool path. So here is going to be the next scenario, right? That allows me to draw the part out, then part it out. And what I did was, if you kind of pay attention to where I was done before I parted, I also left myself enough material for the next part run. So then I could immediately come back down after I'm done working on my sub spindle and start machining the next part. Really, this would be probably the most desirable method once we start to get into some kind of an automated production scenario. All right, so how do we handle the draw function? So it's pretty straightforward. The big thing is I got to think about, I just moved the G54, really. I mean, in theory, I didn't because nothing's changed, but my part location changed. So how do I compensate for that? And there's a bunch of ways we can do it. Now, in this case, I'm going to set up my nesting strategy again. So my my 50 mil projection in this scenario, right? And my grab location. But I do need to think about where I'm drawing it to in the interim. So there's going to be one piece of this puzzle that I got to think about. And where that really comes up is when I've pulled out to a cutoff position, right? So before we've been coming down and we've been grabbing the part at a known location, in this case now 309. But I now need to pull the part out while the main chuck is in an open state. So my M132, it's spinning. I'm going to pull it out. I'm going to reclamp it, but in the interim, I need to compensate for this new move. And this is a case where I like to use the trans command. And the trans command itself is just a linear shift of my 0. So I'm moving the work coordinate system out 103. So what I have to think about is I have to take into account a few extra things in this location. And you see how I added a couple extra numbers here? So in my Z location, I do have to now take into account my overall length after machining of op1 and my insert width, because this is the position I'm drawing the system out to, and that's a critical location. So I've come over, I've grabbed the part at the 309, so how much do I want to pull it back? So think about it, I'm pulling it back, how much stock I have left. I've already taken 1 mil off. Remember, our initial blank size was 102 to start. So I took off a mil when I machined the first op. So I'm going to pull it out 101 millimeters, but I also have to give myself an extra 3 mil. And the 3 mil is coming directly from the part off tool that I'm using. So in this case, I was using, I think, plunge cutter. There you go. I have a 3 mil. So I have to know the insert width when I get to this strategy. So if we're doing it at a cam and we get down the floor, we do want to make sure that whatever value I used in the cam for my insert width mimics there. Now you can certainly give yourself a little extra stock to maybe anticipate some slight variance, but not a lot. You got to be really close here. I mean, this pretty much has to be on. So that's where that number I just came in. So this position, this value, this G1, this is the value I'm pulling or drawing the part out to, because at that point I'm going to close the chuck. And the way I compensate for the fact that I just slid it out right here, 103 millimeters insert width plus the overall part length after op1, that's my shift of my z-axis. So this is just shifting the z in the active work coordinate system, which in this case is G54. I haven't loaded 55 yet. We're not there. 103. Now I can grab it and I can drive my part off cycle as if I'm working from the same 0. So I can still tell the machine what is my overall length of my part. Then we pull back. I do like to cancel the work coordinate shift that I just applied. So I want to get rid of this. And this is a programmable frame, so it's not going to rewrite the work coordinate system. But I do want to cancel it before I do anything else. And then we're going to get into the coupling command, and then really the rest of it is all the same. So I'm going to shut my coupling command off, I retract, and I go through. So if you look at the program, it's getting a little bit longer. So if we come over to the program, and we look at cutoff A, we pull on down. All right, let's get down into it. Okay, so there's the draw command that I mentioned. So I'm still going to feed over, got my coupling, get onto my clamp location, close my jaws, and then we're going to pull out. And again, the big trick here is to compensate for the insert width and the amount of stock material after op1. Right, because I was 102, I took a mil off of it, now I'm sitting at 101. Once I finish the other op, taking the final mil off of it, then I'll be at my desired 100. We shift the work coordinate system by the sum of these two numbers. That's where I got the 103 from. We part it off, so there's the part off, leaving my 101, right, from a part off, because I need to leave the extra mil. I mean, you know, in theory, if you didn't want the turning tool to face off the part, you could bring it to size right now. Certainly, you'll get a much better finish if you use the turning tool. Then we retract, cancel our transformation, load up our new work coordinate. So now when we look at it, we're now going to get the draw. And certainly this is by far probably the most desirable method of machining this part. I can keep it nice and close, just stick it out the max amount I need to. I can have it fully supported during the part off, and then get her back to a nice stable location for, here you go, here we're going to come in. You see the distance I have there is enough to machine the next part. So if the system came down, and that's that workpiece refocus. Just change the view for me so I don't have to worry about doing it. Nice little trick. And there we are. We've now done a full part transfer, withdraw, and cutoff. And really any one of the three scenarios we just showed you are probably going to be your most common scenarios of how you're going to handle picking and placing whatever toolpath and part geometry you're doing at this point. So there's one other thing I want to show you guys before we open up to some questions, but you guys, if you want, you can certainly start typing some questions in. We're going to do a Q&A here in a few minutes. But one thing you can do is, if you want to have flexibility at the shop floor for the operator or the programmer to be able to move things around because the setup's going to change, whether the draw position or whatnot. So this would be a great example of using local variables and linking the local variables to really all those components that I mentioned earlier. So here, this is an example of a header where I'm using a bunch of local variables. So what do I mean by a local variable? It's a variable I created that's going to be in existence only during the running of this part program. If you haven't seen the variable programming webinars I've done two. I would suggest go take a look. I go into this topic in a lot of detail, but this is a great way for me to now give the operator some control over what's coming down through the CAM system. So I'm going to define a bunch of real variables. So I created one variable that's called the underscore G54Z, another one's underscore G55Z. I got my underscore transposition, underscore ZW2, ZI, ZB, ZA, ZI2, and IW. So these are all the local variables I just created. Now, when you're creating local variables, the definition statement's the first thing of your part program. And then you're probably going to want to set these variables, right? So here I have my work coordinate. Those are going to plug into what later was my system frames. So instead of the operator having to go down into the G code to adjust the work coordinate, if he wants to make a tweak to it, he can do it right here in the header. He can plug in the transfer position that he calculated out, or he used maybe that little Excel spreadsheet that we got to do it on. He can define the Z2W location, or the rest position of the counter spindle, what the overall part length is, and then if I want to give some additional bar length because it's really bar stock, then I can do that. That's why I did a little bit of a calculation here. Or if it's just pick and place, it can just be the 102. What you want to avoid, if you are going to be doing bar stock and you're going to be using our workpiece blank, that the part is sitting in space. It needs to be connecting to the jaws. So this is why I'm giving it this ZI. When we look at the part program, you're going to see where that's inside of the workpiece definition. There's ZI2, stock after transfer, the insert cutoff width. So all of this stuff is now allowing the operator to do some tweaks. So if he just needed to tweak the width of the insert, he could come in and he could do that without having to try to figure out where in the program that was. Part projection from the chuck draws and how much material I'm going to be cutting. So once you've set up all these variables, then you can come in and you can start to use them in place of the geometry. So for argument's sake, if we look here, when I was driving the Z2 to the pre-rapid position, well, instead of typing in the 309, I used that local variable in place of it. And then here I use the local variable again. Or, maybe when we're doing the retract, I'm using the transfer position plus the ZI2, right, the 101, which would be the stock length after op1, plus the insert width, and now it knows how much to pull out. And this is where I can now compensate for this quickly in my trans location as well. So this would be a nice way to see it kind of come out of the CAM system, and then this way a user or an operator can gain some more control over that. So before we start questions, let's just take a quick peek at the program. So this is finally B. So just like I showed you, here's our header. Here's our setup for all of our variables, and I would certainly add instructional notes for the operator. If I'm going inside of a CAN cycle, which I can be for sure, I would just replace the numerical value for the new variable. So there's your underscore ZA. That's why I used my designations. Now you don't want to duplicate one of our variables. That's why I'm using an underscore in front of each one. But that's my stock amount, my overall bar length, right? There's the overall bar length. So if I'm sticking something that's going to be floating, make sure you give it a little extra bar length because it does have to touch the jaws. My projection, how much I'm sticking out. And then you can see down here, we're just really going to replace every time I was driving it to one of these locations, going to replace it with that local variable. We come down. A lot of this stuff doesn't require it. This is just the, the turning of that other op. Tool change, and then we come down to our transfer position. So now we're at the transfer location. Later, I come back in to finish my transfer, my draw, my retract positions right here. And then we go and we do our secondary op. So I have a little bit more flexibility. So if we take a look and we simulate, and in she comes. So we're doing our first op. I can kick up the override a little bit. Okay. So there's our, make sure it's moved. So we come over, feed, pull out, do our part off. And then she's going to jump over and do our back op. So if I wanted to do a quick mod of this, now once the operator gets familiar with this scenario, he can just come right up to the top and say, okay, well, I know if I want to change my park location, and we're going to reduce it by 200 mil, I would have to compensate for the new work coordinate. Well, that makes sense. So we could drop this to 580. And just by making those couple quick changes there right in the local variables, I can adapt for any variances, chuck projection. The only downfall is he's going to still have to understand how this nests. So I would say if you're going to do that and you want to be able to have that flexibility on the floor, you would want to have something like that, the Excel spreadsheet that I showed you guys. So this way you can kind of see and use that as a basic setup process. But there we see everything's still working, it's still touching. Certainly if I got that number off like you saw earlier, the insert would not be in position. So there is quite a bit of detail. So I think at this point would be an appropriate time to open up the floor for any questions you guys may have. Again, I wanted to give you my email address. So if you guys want to get a copy of that spreadsheet, shoot me an email. I'd be happy to give that to you. So what kind of questions do we have? Okay, so Joe was talking about how he was doing these in shop turn, and I mentioned again the clamping is not active anymore. And yes, that is true. So what he's referring to when I do it in shop turn, all these calculations we're talking about, it happens automatically for you. So if you're in the habit of coming in and using this values, these aren't taken into account. So what I would suggest, if you're going to go down the road of even setting up those variables, you may want to even pull these system variables into play. So instead of having to hard code them in, we could even add that into the solution. So that would be one thing we could use, and you would still use these. Okay, so Alex is asking a question. If you add in the offset using the coupling on command, will the work offset on the sub spindle after transfer account for this offset? i.e. would the cross cut of the C0. So I believe that offset is only applied during the actual running of the two spindles. It's not shifting the 0. So once you shut the coupling off command, you're still driving from the same 0. I've never seen a case where that did not occur. So like in your scenario, you've indexed at 180. You haven't actually shifted the 0 of the counter spindle 180, just the relationship of the two during the coupling command. All right, so any other questions from said audience? You guys are quiet today. Just a couple. Oh, here we go. My buddy Mike. How we doing, Mike? Can you use the $P underscore tool L index 1 instead of using D0, as you might have a D2 effective for the retract as we do on the mills? Sure, we could. So that is just looking at or accessing the system variable for the tool length. We could do that for the SUPA. I actually prefer, to be honest with you, using the G75 command instead of the SUPA command. The problem with SUPA, as a lot of us know, it suppresses the active work ordinance system, but it doesn't suppress the tool offset by default. There is actually a machine MD, Mike, you might not realize this, that you can change that behavior, but I would suggest not, because all of your machines are all set up with it not suppressing the tool offset. So we do have the ability of using, and just show you guys because this is kind of neat, you can have predefined safe retract locations. They're an Axis MD, and it's referred to as G75. So it is set up in this 30,600 field. So this is also a nice way to drive the machine to a safe spot. So the way this works is you have 4 indexes. Fixed point equals 1 would be the first index, right up through 3. And then whatever number sits in this field for all our given axis, the machine will just go to that location. It's just a quick, easy way to establish a safe retract location. So this would be another solution as opposed to using a SUPA command you might want to explore. Matt is asking, what are the system variables for the chuck data? You know, it's a good question, and I'd have to look them up. I don't remember them off the top of my head. I do believe you can find them in the system variables manual is where I think I saw them in the past. But if you don't see them, just shoot me an email. I'd be happy to dig in and look for it myself. Okay. Any other questions before we wrap it up? So I hope you guys enjoyed the content. We're going to be doing another one in this topic series. Probably not the next webinar. Obviously, we talked about doing the 808, but probably before the end of the year. The next one in this progression is going to be introducing B-axis heads and how do we program a B-axis head in G-code. And then we will wrap up this series probably sometime early next year. We'll do a final one, which will be a multi-channel. So we'll do a full G-code seminar handling multi-channel, B-axis, sub-spindle, all that good stuff. So keep an eye out for that. And it looks like I got all your questions. If I missed anything, you guys have my contact information. As always, please feel free to reach out. And I look forward to seeing all you guys again real soon. Thanks for coming. Thanks for your time. And we'll talk soon. Have a good day. Bye-bye.